In this video, we're going to talk about the graphs of sine and cosine functions, which are also called as a group sinusoids. So these oscillate on a domain of all real numbers, and the parent functions have a range from -1 to +1. Now, why do the parent functions look the way they do? Now that you've learned about the unit circle, this should make a little bit more sense to you. Now, we could loop around the unit circle as long as we want to, but we're just going to record the values that we get in one trip around the unit circle. My x is going to be in radians, and my y for the sine function is going to be what we get when we evaluate this function at different radian values. I'm going to use 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now I could use every conceivable radian value between 0 and 2 pi, or I could use every radian value between -infinity and +infinity. But our point is just to see the behavior of the sine function. We can see its behavior in one trip around the unit circle, which for this function is also considered one period, because it's going to take the sine function from a starting value on the y-axis and return it to that same value after going through an entire life cycle of sine. So, if you'll recall, on the unit circle, the sine value is the y value of the coordinate with that radian value. So if I substitute 0 in for x in the sine function, my y value, after I evaluate that function, is 0. If I substitute pi over 2 into the sine function, my value is 1. If I substitute pi into the sine function, the value is 0 again. If I substitute 3 pi over 2 into the sine function, the value of the function is -1 this time. And finally, if I substitute 2 pi into the sine function, I'm back to where I started, at 0. So, that's why when you evaluate the sine function, if we put each of these radian values on our x-axis and we graph the y values on the y-axis, you'll see sine, the parent function, doing exactly what we expected it to do. It starts above the x-axis, or on the origin, right here, at 0, 0. Then it goes above the x-axis, back to the x-axis, below the x-axis, and back to the x-axis. So that's one complete trip around the unit circle and one life cycle or period for this function itself. Now let's talk about cosine. The main difference about cosine when we look at the unit circle is that it is going to come from the x values on the unit circle. And we're going to use the same radian values in this table to complete a full trip around the unit circle and see one entire life cycle of cosine, or one period of cosine. Now, if I substitute 0 in for x, I'm going to have a y value of 1, because that's what cosine is when you substitute in 0 for the x in this function. If I substitute pi over 2 for x, the value I'm going to get for the function is 0. If I substitute pi for x, the value I get for the function is -1. If I substitute 3 pi over 2 for x, the value of the function is 0. And if I substitute 2 pi for x, the value of the function is 1. So now when I graph this function, I'm going to begin the function's graph above the baseline, the x-axis, then go to the x-axis, go 1 unit below, back to the x-axis and 1 unit above. So I've completed one trip around the unit circle, one life cycle of cosine. I've returned back to where I've started, and we also call this a period. Now, notice that the period for cosine and sine, the distance or the length on the x-axis that it takes to complete one entire life cycle, is 2 pi for both of these functions. Also notice that I labeled my x-axis the same in both of them. And those labels always come in 4s in one period. So we divide the period by 4, and we call these increments. So pi over 2 is the increment that we're counting by, instead of how we usually label the x-axis, counting by 1s or 2s or 5s. We're counting by pi over 2s in this situation. And finally, notice that we're going one above and one below the x-axis, or the baseline here, and that unit of 1 is called the amplitude. Notice that we're talking about how far above and how far below, not the entire height from top to bottom on this curve. So the amplitude is just how high above or below the baseline we're going. So, how do we get these numbers if there have been some changes to the function? And this basic formula could be used for sine or cosine functions. It's going to work the same way. The amplitude that we discussed, or the distance above or below the baseline in a function, is going to be found using the letter a, or the value that the function is multiplied by. And you'll notice that a is in the location where our vertical stretch or shrink is going to be. So if it's a number greater than 1, you're going to have a stretch, a vertical stretch of the function, and if it's a number between 0 and 1, you'll have a vertical shrink. Now if we put a negative sign in front of that, the entire function is going to flip over the x-axis, as you may have expected. Now the next thing that we talked about is the period, or the time it takes a function, that's a sinusoid function like this, to complete an entire life cycle, to do everything it can do, above, below, and back to its starting point. So the period normally is 2 pi, as we saw in our two parent functions. However, this number b can cause the function to be horizontally stretched or shrunken. So to determine the new period, if the b value is not equal to 1, you're going to take 2 pi, the typical period for the function, and divide it by the value of b. And that's going to cause a vertical stretch or shrink. If b is a number that's greater than 1, you'll notice that b is dividing 2 pi, so we're going to have that shrink. So remember, the horizontal stretch or shrink is opposite of what you would think it would be. So if we have a number bigger than 1, it's actually going to shrink. Whereas if we have a number that's less than 1 but greater than 0, the graph is going to stretch, and you'll see that in the examples we get to. Now, a phase shift is the word that we use, or phrase we use, with sinusoids that talks about a horizontal movement to the left or to the right. As we've seen with other functions, that's going to happen after we factor out the coefficient on the x. So in this case, we'd get c divided by b. So the phase shift is going to equal c divided by b, but also remember that it's always going to be opposite of what you would think. So if you have a positive value there, it's actually going to move the whole graph to the left, c over b units, and if you have a negative value there, it's going to move the whole graph to the right, c over b units. Now the vertical shift is going to be controlled, as you may expect, by the value of d. So whatever's added or subtracted to the function, just like in other functions that we've seen, if it's added, it's going to move the function up, and if it's subtracted, it's going to move the function down that number of units. And finally, we talked about the increments in our previous graphs. And the best way to get those increments to put on your x-axis is to take your period and divide it by 2. And that's going to be your best way, or I'm sorry, divide it by 4. That's going to be the best way to label your x-axis so that it's not too tricky working with your fractions. Now let's try this in the function f of x equals 3 cosine of 2x plus pi plus 1. First of all, the amplitude is controlled by the coefficient of the function. So in this case, the amplitude is going to be 3. So we're going to have a vertical stretch of 3 above and below the baseline. The period of the function is, remember, 2 pi normally, but we take 2 pi and divide it by the coefficient on the x. So 2 pi divided by 2 in this case, which is just pi. So we've got a horizontal shrink from 2 pi down to just pi units to complete a full life cycle of cosine. The phase shift is the horizontal move left or right. So for that we factor out the coefficient of the x, and we get the phase shift is pi over 2 units to the left, because we have that positive sign and we always do the opposite of the sign. Remember, you can also do this by dividing c by b, so pi divided by 2 in that case also. The vertical shift is 1 here, positive 1, so we're going to move the whole thing up 1. And the increments are going to be what we get when we divide the period pi by 4. So pi over 4 is how we're going to label our x-axis. Now, when I graph these, the best thing I like to do, or my favorite thing to do, and as you practice this, you'll develop favorites as well, is to go ahead and do my vertical and horizontal shifts first and establish a new origin. So my normal origin with my parent function, of course, is 0, 0. But I'm moving to the left pi over 2, and I'm moving up 1. So that's going to move my baseline up to y equals 1. And because my increments are pi over 4, I'm going to count on the x-axis by pi over 4, pi over 2, 3 pi over 4, and pi. And I can repeat that. This would be 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, or 2 pi. And if we go in the negative direction, negative pi over 4, negative pi over 2, etc. Alright, so I've already moved it up 1, and now that I've got my x-axis labeled, I can move left pi over 2. So this intersection is going to be my new origin. So that's where the function is going to start. And you can graph everything from here on out as if that was your origin for your parent function. Now the amplitude is going to be 3. So I'm going to go 3 above this new origin, 1, 2, 3, and 3 below, 1, 2, 3. And I didn't have a vertical flip, so I did not flip over this new x-axis, the blue line. So I'm just going to start, just like my cosine function does, above the origin. I'm going to go to the baseline, then I'm going to go 3 below the origin, go back to the baseline, go 3 above the origin, and if I draw a sine curve through that, or in this case a cosine curve, I have one period of my function. And I could keep graphing the function by returning to the baseline, going below the baseline, back to the baseline, above the baseline, back to the baseline, below the baseline. You could do this for the entire set of all real numbers. But of course, we don't feel the need to do that. Now, if you graph this in your calculator, to see the function look like this, you're going to have to change your window settings to let the graph count by pi over 4 units. Otherwise, it's not going to look just like this. So that's one thing that can help you. Also make sure that your calculator is in radian mode. Otherwise, it'll look a little bit different than what you expect. So if I set my calculator to have the same domain and range as the graph that I just did, by using negative pi over 2 as my x-min and pi over 2 as my x-max. And notice the calculator does change it into decimals, and that's fine. And I also used pi over 4 as my x scale, or my increment. Changed that to decimal also. Then I used -2 as my y min and +4 as my y max, and counted by ones on the y-axis or y scale. Notice that my graph on my graphing calculator screen looks pretty remarkably similar to the graph on my paper. You want to be able to graph these without the use of your calculator because the calculator is not allowed on the coming test, but that's a great way to be able to check your work in the calculator.